Hi, I'm Dr. Justin Clar. I'm a associate professor of chemistry at Elon University. I have been involved in environmental science, nanotechnology research for the last 14 years at the University of Florida, the EPA, and now Elon.
How did you get involved in this type of research?
I've been involved in water treatment and water quality research for my entire career. Specifically water treatment and dealing with nanoparticles. And so I started working with boron nitride and trying to understand its possibilities for water treatment and water remediation. And I was fortunate enough to connect with the gentleman from BN Nano and started working with the product, which has been very successful.
How did you get involved, or how did it evolve into the PFAS remediation?
So PFAS is a huge problem environmentally. 10, 15 years ago, it was not really on the radar for many folks in terms of potential human health effects like cancers. But over the last 10, 15 years, it has become, in my opinion, the #1 environmental issue that we're dealing with in terms of water quality and water treatment. And my initial goal was to see if boron nitride materials could be a remediation technology that we could use for PFAS technologies. And it turns out that they are an excellent tool to both adsorb, to help remove PFAS materials from water, as well as degrade and destroy PFAS materials using a photocatalytic process.
What exactly are PFAS?
PFAS stands for poly or perfluorinated alkyl substances. So what that means is they're long chains of carbon-carbon bonds, and attached to those carbon atoms are fluorine atoms. One of the ends of these is kind of hydrophilic in nature, which means it loves water, and the other ends of these chemical structures are very hydrophobic, which means they don't really want to be in water environments. So it gives them some surfactant-like qualities, and those qualities make them really great for like nonstick coatings, like Teflon, your raincoats and things. The problem with PFAS is that the carbon-fluorine bonds are amongst the strongest of chemical bonds. They're one of the strongest covalently bonded molecules or bonds we can make. And because of that, it's very difficult to degrade them. So once these PFAS-like chemicals are in the environment, they've been given the phrase forever chemicals because they're so resistant to degradation that getting rid of them in a natural system becomes very problematic.
So what exactly is going on when you mix water contaminated with PFAS with boron nitride materials?
So there's a couple different possibilities or strategies that are going on here with the boron nitride materials and PFAS. The first is adsorption. So that means that we mix it in a container with our boron nitride material and then the PFAS, and the PFAS sticks to the boron nitride. We can remove the boron nitride from the water and you're left with clean water. This works well for small organic contaminants, for dyes, and for some PFAS-like molecules. The other thing that happens that we can have is what's called a photocatalytic degradation. So if we shine UV light on a sample that has both the boron nitride materials and the PFAS, that UV light is going to generate some free radicals on the boron nitride surface. Those free radicals attack the carbon-fluorine bonds, effectively taking these really difficult to degrade chemicals and individually destroying these carbon-fluorine bonds, making these chemicals go from potentially very harmful and toxic to not harmful in the environment.
Now, the EPA guidance or proposed regulations are very small amounts in the parts per trillion levels. How do you test for that?
So in order to test for parts per trillion levels, you need some very advanced instrumentation. And so what we have and what we've been using is a tandem LC-MS-MS, which allows us to do multi-reaction mode monitoring and get very, very low detection limits for PFAS standards and chemicals that we're testing.
And you do these here in your laboratory?
Yes, we do.
Now, in your laboratory, are you doing all the work in the testing, or do you also include your students?
So I do a lot of the work myself, and I'm always including students in my work. That's one of my goals, is to get undergraduate students to get in the lab and see the impact they can have on the world around them, because most 18 to 19-year-olds don't think they have that much power, but this lab work is a very important tool for them to see the environmental impact they can have outside the lab.
Now, PFAS is the focus today, but what else could you potentially do with the boron nitride materials?
So the boron nitride materials in our initial testing have been really excellent at removing things like textile dyes from water through absorption processes. We've also tested some small organic molecules. And based on the research with PFAS, anything that can be photocatalytically degraded could be a target for these boron nitride materials. So these boron nitride materials don't necessarily just degrade PFAS, they could do any kind of contaminant that has this photocatalytic activity, which means the possibility or the suite of chemicals you can destroy using these materials is quite large.
Do you believe there's a high probability of commercializing a technology using boron nitride materials for removing and destroying PFAS?
I do. I think there is a great opportunity for boron nitride to remove and destroy PFAS because this problem is not going to be going away anytime soon. All the nonstick cookware you have in your homes, all the rain jackets, all these materials, they're still out there and they're still being used. And it's not like as soon as we stop using them, all of a sudden that they're going to be gone in the environment. There's going to be fluxes of this material in the environment for decades and potentially longer. And so there's going to need a way to remove these chemicals. And because of the flexibility of boron nitride for the different ways it can be used, the different types of chemicals it can be used with, it could be an excellent water treatment technology outside of PFAS for many years.